Hello everyone, my name is Zhenlong from Zhenlong University. Today it's my great honor to be here to present our recent work. The title is The Frequency Regulation of Integrated Microgrid via Modified Active Disturbing Rejection Control. This presentation contains the 5 parts. First is the background, then I will introduce the integrated microgrid model. In the third part, I will show how to design the modified active disturbing rejection control. In the fourth part, I will show simulation validations. Finally, I will make a conclusion about this presentation. Now, I will show the background of this presentation. With the proposal of carbon neutralization plan, the integrated microgrid is playing more and more significant role due to its low carbon, flexibility, cleanliness, environmental friendliness, and other advantages. So, the following factors should be considered. Firstly, is that the integrated microgrid often contains many components such as photovoltaic, wind power, fuel cell, and the gas turbine, and so on. And the second factor is that the operating quality of the load frequency regulation of the integrated microgrid is significant to the stability of the power grids. However, the intermittence and randomness of the renewable energy, such as the PV power and the wind power, can result in great challenges for the stability and reliability of the integrated microgrid. Besides, the uncertain customer load also disturbs the load frequency greatly. Therefore, how to improve the control performance of the frequency regulators is becoming a much more important topic for the integrated microgrid. To better improve the control performance of the frequency regulation, many control structures have been designed for the integrated microgrid, such as the PID or fractional PID controller, sliding model control structure, model predictive control structure, reinforcement learning control structure. These control structures all have some advantages and some disadvantages. Take the model predictive controller as an example. It can obtain the satisfactory control performance under the nominal conditions, but when the operating condition is far from the nominal condition, the control performance will decrease greatly, and the model predictive controller also needs the precise mathematical model information. The PID controller, sliding model controller, and the reinforcement learning controller also have the similar conditions. Now we may have a question: which controller is suitable for the frequency regulation of the integrated microgrid? We can make a summarize about the suitable controller for the frequency regulation. Firstly, it should have a simple structure and it can guarantee the reliable control performance. It also has the simple turning rules and easy implementation, and it should have no requirements about the precise mathematical model. Based on these requirements, we found the ADRC, or named Active Disturbing Rejection Control, is a suitable controller for the frequency regulation. ADRC is proposed by Professor Han with the total disturbing rejection idea, and it contains the extended state observer ESO, SFCR, and the TD. Based on the ADRC's idea and structure, the theoretical analysis such as the convergence of the ESO and the system stability has been done. It also has been applied to the power systems, motor systems, and many other industrial systems, and show a good application proposal. Now I will show the integrated microgrid model. The integrated microgrid system contains the wind generation systems, the photovoltaic generation system, the flywheel energy storage system, battery system, fuel cell system, and diesel generation systems, where their dynamics can be modeled by different transfer functions, as shown in the following equation, and the structure can be shown in the figure 5. Based on these systems' transfer functions, we can obtain the diagram of the load frequency control for the microgrid as shown in figure 6. Then we can obtain the customer load is decided by the following equations. Then we can have the frequency deviation, which is decided by the last equation. Then we can also have the open loop step response of all subsystems as shown in the figure 7. We can know that different systems have different dynamics. So when we design the controller for the frequency regulation control, the following factors should be consulted. First is the different dynamics of subsystems. We should balance the different dynamics. And second is the system output are limited. Based on the control structure of the regulation in Figure 8, a modified ADRC is proposed where a compensation part, GCPS, and an amplitude limit are added before the control signal is sent to the ESO as shown in the figure 9. The modified ADRC can foster the step response and can enhance the disturbing rejection ability, and it also can avoid the actuator saturation. Based on the structure of the modified ADRC, and we should make some analysis about the system stability, and we have the theorem 1, where the observer estimate error is bounded with some assumptions, and the proof process is complex and is omitted here. Before a new controller can be applied to the practical, how to obtain the controller parameters quickly and efficiently is important. And this requirement is also estimated for the modified ADRC. To obtain the turning rule for the modified ADRC, we applied the single variable method to analyze the influence on the control performance with different parameters. We also carry out lots of simulation. We summarize the turning procedure as shown in the figure 11, where the turning procedure is easy and practical. Based on the proposed tuning procedure, we can obtain the modified ADRC parameter as listed in Table 1 as the comparative controllers, the PID original and the PID optimized by the GA algorithms named PID-OP, and their parameters are also obtained and listed in Table 1. Besides, we also need some performance indexes such as the IE, ITAE, IE, ISE, and the ITSE to manage their control performance. Now we can show the simulation result in case 1, where the PV power, wind power, and the consumer rate have step changes without management noise, as the results and outputs are shown in the Figure 12, and the control performance indexes are also calculated in and listed in Table 2. We can know that the modified ADRC has the strongest disturbing rejection ability, and the modified ADRC needs the least time to recover to the steady state. The jet of the control signal for the modified ADRC is much less than that of the PID-OP. Now we will show the simulation result in the case 2. The PV and the wind power have step changes with management noise, and the consumer load have step changes without management noise. The results shown in the Figure 13, and the control performance indexes are listed in Table 3. We can know that the modified ADRC also has the strongest disturbing rejection ability. The modified ADRC still needs the least time to recover to the steady state. The zeta of the control signal for the modified is less than that of the PID-OP. Now we will show the simulation result in case 3. The PV power and the consumer load have step changes with management noise. We can know that from the Figure 14 and the Table 4, the fluctuation range of the modified ADRC is the smallest. The fluctuation range of the PIDO is the largest. Similarly, we also have the same conclusions of the case 4 as the case 3, and the output in Figure 15 and the control performance indexes in Table 5 also verified our conclusions. Finally, we will show the simulation result in case 5, where the PV power, wind power, and the consumer load have step changes with the management noise. The results are shown in the Figure 16, and the control performance indexes are listed in Table 6, where it can be known that the modified ADRC can reject the power outputs of the winds and the PV, while the frequency variation of the modified ADRC is the smallest. In total, the modified ADRC obtains the best control performance for the integrated microgrid. However, the system uncertainties, such as varying operating conditions, system nonlinearities, and necessary model simplifications always exist and can elevate the control performance. Therefore, the ability to handle system uncertainties should be considered when we design the controllers. And here we applied the Monte Carlo trials to compare the controller robustness of all controllers. and we can obtain the result of Monte Carlo trials in cases 1, 2 in figure 18. And the figure 19 shows the results of Monte Carlo trials in case 3 to 5. Notice that more concentrated indexes result in better controller robustness. Similarly, smaller indexes result in better control performance, and vice versa. Now we can, based on the results of Monte Carlo trials, we can conclude that the first one is that the modified ADRC has the similar control robustness with PIDO and both better than PIDOP. And we also conclude that the modified ADRC has the best control performance when the system is uncertain. Now we can make a conclusion about this presentation. Firstly, based on the analysis of the load frequency regulation model, we proposed a modified ADRC for the load frequency regulation of the integrated microgrid. Then, based on the modified ADRC structure, the boundedness of the observer disturbing area is analysis theoretical. Then, we also provided a practical and effective turning procedure. Based on the turning procedure, we can obtain the modified ADRC parameters, and we can also have the comparative controller PIDO and PIDOP parameters, and then the simulation in different cases can be carried out, and the effectiveness of the proposed modified ADRC to reject the disturbing from the PV power, wind power, and customer load is validated. And the future work of this presentation will focus on the adaptive operating conditions for the modified ADRC, and then we will apply the modified ADRC for the integrated microgrid test bench. This is the acknowledgement for the funding support. That's all. Thank you. Any questions?